Hello. In this video we're going to be going over Chapter 16, Lecture 14, Learning Objectives 5 and 6. So we're going to be looking at relative acid strength, or acid strength relative to their bases and each other, and then we're going to look at Lewis acids and Lewis bases. So our acids themselves, we can look at two different types of acids, binary acids and oxyacids. With binary acids we're looking at bond strength when we're comparing elements in the same group, and then bond polarity when we're comparing elements in this different group, same period. So, for acids in the same group, we compare bond strength. So we're looking at an HA bond. And our binary acids are those HA acids we've looked at, where A is a single element ion, or anion. Okay. So the stronger the bond, the weaker the acid. So as we go down a group, our ion or anion size gets larger, so our bond strength gets weaker between our anion and our hydrogen. So going down a group, our bond strength decreases, our acid strength increases. Okay, so hydrofluoric acid, for instance, is a weak acid, while we go to hydrochloric acid being a strong acid. Hydrobromic acid is stronger than that, and then hydroiodic acid is a very strong acid. And then for acids that are in the same period, we look at bond polarity. The more polar the bond, the more electron density that's getting pulled away from our hydrogen ion, or proton, the stronger our acid, because the easier it is for that hydrogen to remove itself as a proton. Okay. We also have oxyacids. These are going to be our polyatomic acids. And we look at two things. We're either going to look at the electronegativity of our non-oxygen atom or the number of oxygen atoms that are there. So our oxyacid, it has some amount of hydrogens, and then we have some atom, or we have some other element, and then we have oxygens. Sometimes we have two hydrogens, sometimes we have one, sometimes we have three, and then we have varying numbers of oxygens between 2 and 4. So we look at the electronegativity of the A atom. The more electronegative, the stronger the acid, because we're pulling electron density away from the oxygen, which then pulls electron density away from the hydrogen, making it easier for that hydrogen to leave as a proton. Okay, so we have some, it's usually something like this that you'll see, where you'll they're looking at this bond strength. So as you increase the electronegativity here, it pulls electron density in that direction, which pulls electron density in that direction, which makes that proton more positive, easier to remove as a H+ ion. Okay, also the number of oxygens bonded. The greater the number of oxygens, the stronger the acid. And this has to do with the stability of the conjugate base. Okay, so let's look at this. We're going to compare HBr and HI, and we're going to identify which one is a stronger acid. This one would be our stronger acid, and that's because iodine is larger, which means that it has a weaker HA bond, so it's easier to remove H+. Okay. Additionally, I- is a more stable anion, which means less reactive, so less basic. If we're looking at HClO3 versus HClO2, this one has 3 oxygens, this one has 2 oxygens, so this would be the stronger acid. Has more oxygens, so we're pulling more electron density away from our oxygen-hydrogen bond, and it also has greater resonance. So our conjugate has more resonance forms because it has greater number of oxygens, so it would be a more stable anion, which means it'll be less reactive, which means less basic. Okay, next one, we're comparing H3PO4 versus H3ASO4. Phosphorus is more electronegative, so this would be the stronger acid. So because it's more electronegative, it's pulling more electron density away from it, and that oxygen-hydrogen bond is becoming weaker. Okay, let's move on to Lewis acids and bases. So we're going to go through a couple of different types of acids and bases and look at the organic versus organic acids and bases, and then specifically Lewis acids and bases and some other things. So the rest part of this chapter, we look at our different types of acids, our different acids we haven't looked at so far. An organic acid is going to be one that contains hydrogen and carbon. And one such acid is a carboxylic acid. So we have some R group, carbon, double bond and oxygen, oxygen and hydrogen. This would be the acidic hydrogen. So this would be an organic acid. And then anything that contains this group, doesn't matter what the R group is, we consider that an organic acid, and we call that a carboxylic acid. Okay. And then if we have an organic base, we have a base that contains nitrogen, it also contains, hydrogen and carbon, and nitrogen. So if you see that nitrogen, you know you're talking about a base. If you see the oxygen, it's an acid. So both of them contain carbon and hydrogen. The bases contain nitrogen. The acids contain oxygen. Of course, if you take the acid and you remove a hydrogen, it becomes a base. If you can take the base and you add a hydrogen, it becomes the acid. So we have some R group, and then nitrogen. That nitrogen has a pair of electrons. Okay, and nitrogen will have 3 things around it, so there'll actually be additional things here, right? Doesn't really matter what they are. So, some examples of some organic acids. We have CH3CO2H. So we should have seen these already. This is acetic acid and benzoic acid, which we've looked at before. And we can also, if we take organic bases, such as NH3, another base we've looked at before, or CH3, CH2, NH2, those are examples of bases. Now, if we take either of our organic acids, remove a hydrogen, we produce a base. Either of our organic bases, we add a hydrogen, it becomes an acid. So NH4 plus would be an example of a organic acid, as would CH3, CH2, NH3 plus. And then for organic bases, if we take the 2 acids we saw above, remove a hydrogen, we make a base, CH3CO2 minus, or C6H5CO2 minus. So both those would be examples of organic bases. And a lot of times those are considered Lewis acids and bases. A Lewis acid is going to be an acid that is electron deficient. So it needs a pair of electrons to complete an octet. Such as with BCl3, this has an empty orbital right here, and it only has 6 electrons around it. So this empty p orbital can accept electrons. Okay. And if it has an empty p orbital, it's considered a strong Lewis acid. We also have Lewis bases. Lewis bases have a lone pair of electrons. Okay. And they're generally in an sp3 orbital. Okay. They are going to be, that pair of electrons is going to be on a highly electronegative atom. And if we have both of these things, we have a strong Lewis base. Okay. So in the case we have here, so remove this. This pair of electrons can donate electrons here to make a bond. This would be our Lewis acid, or sorry, Lewis base, and our Lewis acid based on our definition, right? A Lewis base donates electrons, Lewis acid accepts electrons. As a note, metal ions are also often potential Lewis acids because they have all those empty orbitals. So metal ions are usually Lewis acids. And the reason for this is because they have empty orbitals that can accept electrons, and they are positively charged. Okay, and what we see with our metal ions is what's called the inductive effect. So when a Lewis base comes in, we get the inductive effect where electron density goes in from our Lewis base and it's pulled towards our Lewis acid. So our metal ions that are Lewis acids are generally highly charged. And of course positive. And that high positive charge is going to pull electrons from our Lewis base to our Lewis acid. That, in turn, makes this, as we pull that electron density, makes this bond weak. And that becomes an acidic proton. Okay? So, when we have a highly charged metal ion, it attaches to a Lewis base. That Lewis base, its electron density goes towards that highly charged ion, and that weakens any oxygen, hydrogen, or nitrogen, hydrogen bonds, making a very acidic proton. And that is how it becomes an acid in water. Okay, so when we take something like iron 3+ and we add it into water, the metal ions form a complex with water. We call this complex a complex ion. It's going to be highly soluble, and it's going to contain a Lewis acid and Lewis base. So something like this, where we have our Fe3+ in the center. That is our Lewis acid. And then our Lewis base, the water's around it, and it will react with water and produce hydronium. So, sorry. We have something like this. Iron hexahydro species with the 3+ charge. When it reacts with water, produces this species and hydronium. We can see this with copper as well. So a hydrated copper species, tetrahydrate, will react with water, and it'll produce this copper water hydroxide species and hydronium. So these hydrated metal ions are very acidic in nature. So let's see if we can identify our Lewis acid and our Lewis base, and then predict the products. So if we have Cl- and ACl3, hopefully you recognize that Cl- has, we actually should draw the Cl-. It looks like this, and then the ACl3 looks like this. We see from here that we have an electron deficient aluminum and an electron rich chlorine. So this pair of electrons will donate to the aluminum, and we produce this following species. We have a negative charge on our aluminum and an overall negative charge. Okay. BF3 plus F minus. We have that right there, boron trifluoride. And again, this is a species where we are electron deficient. We add in F minus, species that is electron rich. An electron pair. We'll donate there, and we will produce this species here, again with a negative charge. NH3 plus H2 or H plus. Here we have this electron pair here, which will donate here, producing the species here, ammonium. You can try the last two on your own, but each of them, well, actually I'm gonna do this one. SO2 plus H2O. Hopefully you recognize this sulfur is fairly electropositive, the oxygen electronegative, so we're going to pull electron density from here, donate there, and then generally push that electron density there, and we get this right here. And a neat thing that happens here, since we have this oxygen and this hydrogen so close to each other, so let's go with what color? Let's go with red again. This pair of electrons is going to make a bond here, pushing that direction, and you get SOH, oxygen there, double oxygen, and then that species right here. Okay, that's everything for this video. Hope you guys, it all makes sense. Try this one on your own, and I'll see you guys later.